The following video recording has been made possible by Robotic, complete warehouse automation. From integrated supply chain consulting to fully automated picking systems with progressive financial models. Robotic systems are deployed in major grocery, retail, and general merchandise operations throughout North America. Learn more at robotic.com. And by Duchin Productions, broadcast, corporate, and web video production services specializing in science and technology. Start the conversation today. Visit DuchinProductions.com to learn how video can get your business the customers, talent, and investors you've been looking for.
I'm going to talk a little bit about some of our more recent updates in our work on soft wearable robots to assist with mobility, so people who are walking, as well as people with upper extremity disabilities as well. So a big part of our research group over the last fall has been focused on this concept of a soft exosuit. The basic idea is, can we apply very small to moderate levels of assistance in parallel with a person's underlying musculature in order to help reduce the amount of effort that a person has to do and take that strain off their muscles and soft tissue. So this has been a big DARPA program called WireWeb, and we've been working on it for about 4 years at this point, and we've been targeting people who are carrying heavy loads from walking over long distances. So we're assisting the hip and ankle joint. This is one of the more recent embodiments of a system that we've built. You'll notice that the soft exosuit is a little bit different than a rigid exoskeleton. There's no metal structure in parallel with the legs. It's not transferring load from the backpack down to the ground. The person's skeleton is still taking that load. But we're basically trying to offset the amount of work that's being done by the muscles at the ankle joint and at the hip joint to help them walk with less effort. And so the big challenge here, you can see that there's a number of components. There's nothing inside the backpack. There's 2 actuator packs that go on the side of the backpack or could be worn around the person's waist. We have textile components on the legs that allow us to anchor securely and comfortably to the person to apply forces across the joint. We have sensors in the system that monitor how the person moves, and then a control algorithm that determines when to deliver the assistance at the right time in the walking cycle to help person while they walk. And you can really think about an analogy as it's kind of simple like a swing. So walking is a very dynamic process. With a swing, if you want to keep it moving, you just give a tap at the right time, and that helps it moving forward. And so recently we kind of published a paper where we evaluated, does this system actually make it easier for a person to walk? And when I was a graduate student at MIT, I worked on a rigid exoskeleton program with Hugh Herr, and we kind of realized firsthand how hard it was to make it easier for a person to walk using wearable robots, and it's been one of the grand challenges in the field of wearable robotics. But recently we showed that we could make it 7% easier for a person to walk when wearing our device. So this is accounting for the weight of the system. The system weighs about 6.5 kilograms, and we showed that we could get a 7% benefit when accounting for that carried weight. So basically what we're showing now, and Hugh Herr at MIT, and Steve Collins and Greg Sawicki, and Samsung actually as well, have shown that with these types of wearable robots, we can actually make people walk more efficiently. And I think we're continuing to work on this DARPA program to try and see really how much better can we get. The DARPA goal is 25%, so can we actually help people walk with significantly less effort? So, here's a video of some ongoing work in the lab. We also do a lot of work focused on people walking on a treadmill in the lab and kind of understanding the biomechanics around that. So you can hear the actuation system here applying force in synchrony with his gait while he's walking. There's no carried load in this case, and for this experiment, we're able to show that we could help someone walk with almost 23% less effort when walking on the treadmill. So that's a pretty big difference. So if you think about kind of some of the other applications of this, if elderly people or other people have a hard time moving around because they get fatigued, systems like this might one day help people move around and stay engaged in their community. We're also interested in outside applications. So this is a simplified version of a hip-only system. So it's only assisting the hip joint, not the ankle joint. We think this is a lot more practical in terms of, eventually kind of having it be used in a field setting. This is obviously some of the conditions that we're testing these devices. This is outside the lab in the winter a couple of years ago. And so you can see developing control systems that make sure that the system is always in synchrony with the person's own natural gait, being able to walk around going up and down slopes, going up and down stairs. And our approach is really try and keep these systems as simple as possible. We don't want to make them very complicated. We just want to give a little bit of assistance at the right time. The nice thing as well is that these systems can get out of the way of the person when they're walking. Because we're using cables, And if you're stepping over obstacles, then the system can become mechanically transparent or just get out of your way completely and very easily due to its kind of soft design. So a lot of this has really been enabled by, we've built up a lot of expertise in functional apparel design. So this is something that I'm not trained in. We have some great people in the lab who have expertise in this area, but we now have 7 different sewing machines in our research group, and we're a robotics research group. And we have people who really understand different materials, how to fit things to the body, how to develop garments, and how to pattern things so that they fit people of different shapes and sizes. And I think this is one of the areas in wearable robots that has often got overlooked in the past, is the interface and the coupling to the body. And because that's really, getting that right really makes the systems perform much better. We've worked with New Balance as part of this as well, so they've been part of our DARPA program, and that's been a great relationship, and they've helped us understand, using different materials, helping us understand how you go from, a concept design to actually getting a vendor or a company make something for you. So we know how to do that for mechanical engineering with SolidWorks and drawings, we know how to do that for electrical engineering, but we've also built up the expertise of how to do this for textiles as well. And you develop text packs, you hand it off, you get parts back in different sizes so you can run experiments on people. So that's kind of an overview of our DARPA work, and we have a lot of work ongoing in the lab around that technology. And a big effort as well over the last 2 or 3 years has been focused on medical applications. So how do we apply the same technology to people with some kind of physical disability? And we've been focused on stroke. And the reason for that really is, if you think about rigid exoskeletons, they're amazing. This is a system from Rewalk that's shown here in this video, helping people who are fully paralyzed be able to walk again. When I was a grad student, I thought that this would take a very long time, but it's amazed me how quickly we've got to this point. But there's still a large number of people out there in the world who can walk, but just not very well. And so an example, population is people who have suffered a stroke, and the elderly, people with multiple sclerosis, Parkinson's disease, cerebral palsy. So there's really a big list of people who maybe aren't served by these rigid exoskeleton technologies because they're essentially overkill. So our goal is, how do we develop a soft exosuit initially targeted at stroke patients that can assist the paretic leg or their impaired leg? So stroke patients have one leg that's usually more impaired or more severely impaired than the other. So can we assist just the ankle joint of that impaired leg, and can we have a big enough difference on their mobility and maybe even help them in the future, retraining them how to walk again? So this is kind of how the system works. It's the same concept. You have an actuator pack that's worn around the waist, and then cables that transmit forces down to the ankle joint through the use of textiles. So this is kind of a picture of our latest system. It weighs in total just under 5 kilograms, so it's still a little bit heavier than we'd like, but it's manageable in terms of having someone walk around with this. Most of the weight is around the waist, which is easier for people to carry weight there. It's hard if you put weight on people's legs. And it's basically the same idea. We have a bunch of different sensors that monitor movement of the person and that help them walk. And so this next video just kind of illustrates some of our latest footage. So you can see here a person walking on the treadmill. We have great people that come in and participate in our studies. And then you can see when the system is put on, they're really able to walk with a much more natural type of walking pattern. And this is simply just by targeting the ankle joint of that person during locomotion. So this is an illustration of the Wyss Institute Motion Capture Lab. And this is where we have our participants come in. We have them walk on the treadmill with the suit and without the suit, and then we try and assess basically how the suit can improve their performance. And we have a lot of ongoing studies in this area specifically at the moment. In terms of translation, recently in May we announced an exciting deal with Rewalk Robotics. They're a local company in Marlborough here, where they've licensed the technology from Harvard, and now they're going to work on developing a translation plan to basically figure out how to bring this to be a product on the market. So we've started to work with their R&D group and their group out here in Marlborough as well. So switching gears a little bit, another area of focus that we have is in the area of assisting the hand or the upper extremity. So this is work that we've had going on kind of really thinking about it from a pathology agnostic point of view, where there's many different people out there in the world who have some kind of who have some kind of issues or physical impairments that prevent them performing activities of daily living. And so we've been developing a soft robotic glove in collaboration with George Whitesides, Rob Wood, and others at Harvard, to really think about how do we use these soft inflatable actuators that people have been developing and apply them to wearable devices. And it's the same basic idea. We don't want to put a big heavy device in the hand. We want to put something on the hand that's comfortable, easy to wear. And we've been going through multiple different iterations of this. And I'll just talk about some of our more recent work. So more recently, we've been moving away from elastomer or silicon-based actuators. They have a lot of merits, but we've been exploring the use of textiles, and can we use anisotropy in the anisotropic properties of a textile to really generate different types of motions that allow you to apply forces to a person, and also thinking about how do you use really cheap materials. We don't want to use expensive materials. We want to make these devices very affordable and very low cost. So it's basically just balloons and textiles. And the nice thing about these fabric-based actuators is that you can go from something that is really truly flexible in fabric and non-restrictive to something that when you inflate it, it can really stiffen, it can take a shape, it can apply a force that's really quite significant. And we're kind of getting better and better at all the time about how we learn to do that. And so what this enables then is for someone who has some kind of physical impairment, like this gentleman who's one of our study participants here, who has a hard time lifting up this object and letting it go, when the glove is worn, the idea is that the person is going to be able to perform an activity of daily living that they normally wouldn't be able to perform because they're wearing the glove. So it increases their ability to grip an object, grasp an object, and perform some kind of common task. And in addition to this kind of qualitative work, we're also working with some clinical partners, Sabrina Paganoni at Mass General, to quantify the increase in performance with these types of systems. So using different standard physical therapy or occupational therapy tasks that someone would use to try and understand how much better is a person with a glove, to really prove kind of the value across different populations. Going forward, one of the things we want to do as well is make these kind of devices smart, so integrating sensors. So here you can just see some early work looking at sensors integrated into a glove. So eventually we can not only assist someone, but we can also monitor their performance, and we can see how they're getting better and kind of assess that over time. And these systems might actually enable rehabilitation in the home or in the community. So at the moment, people have to come into the hospital to get rehab, but what if you could actually do that in the home? That would really be exciting. But we want to make systems really easy to use and really cost effective for that. So I'll just conclude with a plug. So we have another initiative that's more focused around supporting research, education, and outreach called the Soft Robotics Toolkit. So if you go to softroboticstoolkit.com, you can check out our cool website. We've been doing this for about 2 years. It basically has multimedia tutorials, content, anything that you would need to get started and build your own soft robot. So it's really aimed at research groups and then also teachers and high school students. And we've had a lot of interest in this, and we are getting close to 1 million page views so far. And we've run competitions for the last 2 years where we've had almost 500 participants participate in competitions. A third of those are high school students who kind of design their own cool soft robots. And we've had 2 competitions. One is a research competition. So for anyone who's working on soft robotics research, you can upload new content. And then we have judges, external judges, who basically kind of evaluate the kind of content as well as how well it's documented and award prizes around that. And then we also have competitions that enable people to use material on the toolkit to develop something new or interesting. And it doesn't have to solve a real problem, it can just be something fun. One of my own personal favorites is we had a high school student in Missouri and basically developed a teddy bear that hugs back. So it's basically a teddy bear with a chamber inside with some soft arms, so when you hug it, you kind of generate pressure in the arms and they bend and wrap around you. And I just thought it was a really cool use of kind of this approach and this technology as well. So beyond that, we're developing instructional materials that people can use, and we'll be putting these on our website as well. And then we've been running some workshops with high school students too, to be able to kind of encourage people to get involved in science and engineering and technology. And I think soft robotics is a really cool way to do that. So with that, I'm happy to take a few questions. Thanks.